Hello everyone and welcome to our next lab. This lab is going to be called Changes in Energy. In this lab we're going to be talking about gravitational potential energy and kinetic energies. Okay, the lab objectives. This is taken directly from the lab handout. And they state that by the end of this lab we want you to be able to relate the gravitational potential energy of an object to its position and determine whether the potential energy increases, decreases, or stays the same in a given motion. We want you to be able to relate changes in potential energy of a given simple system to changes in an object's speed. And we also want you to be able to calculate gravitational potential and translational kinetic energies for simple situations. Okay, first off, what is energy? Energy in physics is the capacity for doing work. It may exist in forms like potential energy, kinetic energy, thermal energy, electrical energy, chemical energy, nuclear, or many other forms. In this lab, however, we will only be looking at gravitational potential energy and kinetic energy. Okay, first off, let's talk about what is gravitational potential energy. Gravitational potential energy is energy an object possesses because of its position in a gravitational field. So I'm sure by now you guys have talked about this in class where potential energy is mgh, where h is the height off the ground, which sometimes we call zero. Mass is, m is the mass, g is the acceleration due to gravity, h is the displacement from zero. Like I said, here in this picture it shows zero as being the ground, but it could be anywhere. We can place it wherever we want, which is a nice part of potential energies. Notice that we have a delta in there. The delta PE equals mg delta h. That means your change in potential energy equals your mass times gravity times your change in height from zero. Now, what does delta mean? Delta means final minus initial. I know we've said that about, I don't know, 100 times since the beginning of the semester, and yet I still see people getting that wrong. It's always final minus initial. Because we're looking at a difference, we may be flexible with where we call zero, where we call zero energy. And potential energy, we can have a negative potential energy, and that is just fine. Now, what is kinetic energy? In physics, kinetic energy of an object is the energy that it possesses due to its motion. Kinetic energy equals 1/2 mv squared. And of course, units of both potential and kinetic energy are in units of joules. You cannot have negative kinetic energy. And why can't we have negative kinetic energy? Because, well, we can't have 1/2 is a positive number. Mass, you can't have negative mass. And you can't have negative velocity, but when you square it, guess what? It's positive again. So you cannot have you cannot have negative kinetic energy. If you have zero velocity, of course you have zero kinetic energy. Okay, conservation of energy. What is conservation energy? The principle of the conservation of mechanical energy states that the total mechanical energy of a system, that is the sum of the potential plus kinetic energies, remains constant as long as the only forces acting are conservative forces. Now, gravity is considered a conservative force. However, we do have things that slow us down in the real world, like friction and air resistance. So in the lab, we assume no friction, but you will see the effect as small differences in what you see and what you expect to see. So if you think it should be a little bit higher at the end of a track, then the velocity should be higher at the end of a track, and it's not quite there, you know why. It's probably due to friction. We can't get away from that. All right, so the equations. That kinetic energy plus potential energy equals a constant. So if you look at the little picture there, you have kinetic energy is at its highest at the bottom of the hill. At the top of the hill, it stopped, so it has no kinetic energy, but its potential energy is the highest. And notice that the kinetic energy and the potential energy have the same height on their bars. Now, if you look at the third part of the picture, where it's part way down, where the kinetic energy and the potential energies are the same, if you add them together, it'll be the same as the potential or the kinetic was when they were at their highest. And you can notice that as one goes up, the other goes down. So the thing I want you to take away from this is that the kinetic energy is constant. That means if you call your zero potential energy where there is zero kinetic energy, then they will always add up to zero. If you have high potential where your kinetic is zero, then they will always add up to whatever the potential energy is. Now, the deltas, this is the same thing. The change in kinetic energy is the negative of the change in potential energy. So as you gain kinetic energy, you lose potential energy. They're going to go up and down, and they're going to be related to each other. Hey, I found this really good example of how this works. In this example, we will call the ground level zero potential energy. The energies will always add up to 10 joules. So if you have a height of 5 meters, and of course your gravitational potential energy equals mgh, you have a 0.2 kilogram baseball that's 5 meters off the ground. Your gravity is 10 meters per second squared, rounding, so that's about 10 joules. Your kinetic energy at the very top, of course, is zero because you haven't let go. Now, total mechanical energy is your kinetic plus your potential, and so that's 0 plus 10. That ends up to be 10. Let's see here. We could also easily call the initial position of the ball 0. So if we said that at the top, right here, if we call this place here 0 potential energy, then they would always add up to 0. So if you gain 10 joules, as you gain 10 joules of kinetic energy, you will lose 10 joules of potential energy, and you'll always add up to 0. Okay, here the ball falls 1.25 meters. And so you plug everything in, you have 7.5 joules of potential energy, but your kinetic energy is raised to 2.5. And of course, 7.5 plus 2.5 is going to be 10. And in this next slide, the ball has fallen halfway, so it's lost half of its potential energy, but gained that much of kinetic energy. Here we have 5 joules plus 5 joules equals 10 joules. And then the instant before the ball hits the ground, it has the same kinetic energy as it had potential energy in the beginning. Okay, notice the pattern? Really, I mean, this is what this lab is all about. And yes, you're going to see questions about that on both a rat, a cat, or a final. Okay, let's talk about our lab equipment. This is another camera lab, so we've already done 2 of those. I believe this will be, I don't think we have one more after this, perhaps. This is what we're going to be doing is you're going to have, we're going to be using the carts. So we'll have the track, we'll have a couple of different tracks set up, and you'll see a steep and a shallow track that'll be right next to each other. And there will be the little cart that has the blinky on it, and we'll be doing the pictures. As you take a picture of it, you can see the flashes as it goes down. You can measure the length of the vectors of the steep and the shallow tracks. But yes, you will be looking at velocity vectors again, because that's what we do. Now for a couple of things to think about. How does gravitational potential energy change when a ball is rolling on a flat surface? What does that mean for the kinetic energy? And then a second thing to think about is using the conservation of energy. How can you prove that when you toss a ball upwards and it comes back. At any height, the speed of the ball going up is the same as when it's coming back. So when you throw a ball up, it goes up, it comes back down, and that the ball that it left your hand at is going to be the same as when it comes back and you catch it. It's assuming that you catch it at the exact same height. These concepts are very important, and they're used throughout physics. I mean, all throughout physics, and it's a good thing. It's a good thing to know. So, anyhow, be prepared for this next lab, and we'll have some fun. Talk to you guys later. Bye bye.